Okay, so as promised in the first video, we're going to go into the details of the different kinds of fronts, starting off with cold fronts. So cold fronts occur when, again, the warm air is advancing forwards or towards the boundary, towards the front. On a weather map or a surface analysis, these are denoted or written out with blue lines with triangles on them. And the triangles point in the direction of the motion of this front. And if we were to think about what this means in a weather sense, this cold air can act like a wedge that forces warm air upward. And if that warm air is moist or unstable enough, it can form convection. So you get things like thunderstorms along that boundary. However, doesn't mean that always happens with a cold front. Sometimes the air isn't quite warm enough, moist enough, unstable enough to form that kind of convection. And you sometimes just get clouds if there's some moisture that it condenses out to form clouds. Or sometimes it's dry enough where you don't even get anything and you just get a rushing, advancing set or area of cold, windy air coming in. On a analysis plot with station models, like we can see from the Iowa Environmental Mesonet, it looks something kind of like this. You have your cold air, cold temperatures over on this side, warm temperatures over here, pretty clear boundary between them. And if you look at the winds, you can see a definite wind shift between these two different air masses, and your cold air is generally going toward the boundary. If we were to predict or expect where this would be in the near future, because the cold air controls the movement of the boundary, it being more dense, we'd expect the boundary to move from where it is about here, probably a little bit further east. If we instead talk about now warm fronts, sort of the opposite, warm fronts occur when the cold air is retreating or moving away from the front. On a map, we denote this with a red line with half circles. Half circles, again, sort of pointing in the expected direction of motion based on where the cold air is. And thinking about this slightly differently than what we expect from a cold front, warm fronts instead have less steep slopes, and because of their direction of motion, they act more maybe like ramps over which warm air can ascend and possibly condense if it has enough moisture. And especially if it's moist enough where we have generally unstable air, it can reach its threshold point of enough buoyancy where it just starts billowing upward, and you get things like thunderstorms forming along the warm front. If there's enough moisture that you get condensation and you get clouds, but it's not unstable enough to form convection, then you can just get more gentle or generally forced convection, forced precipitation, my bad, where you get things where you just get precipitation and not thunderstorms happening. Either of these can easily happen on warm fronts. If we were to take a look at a map, now it might be a little bit confusing because, again, this is where the cold air maybe doesn't want to move as much. It doesn't have as much forcing because the warm areas has a lot of the dominant activity. But there still is some component of the cold air moving away from the boundary, so it still is considered a warm front. And again, you can sort of see warmer temperatures over here, colder temperatures over here. This particular example doesn't have quite as strong of a contrast, but you still get the general idea. Stationary fronts instead occur where the cold air is mostly stationary near the boundary. So you get things like calm winds or barely any winds near the boundary. But if we were to talk about the weather that you interpret from a stationary front, it's very similar to how a warm front would behave, except from a forecast sense, it's not moving. So whatever you're seeing will probably continue to happen in some way or another because this front just isn't moving. It's stationary front. So there's another sort of combined type of front that we want to talk about, is what happens if two fronts collide with each other. This is where we get something called an occluded front. And typically this happens because cold fronts with cold air behind them are moving faster than warm fronts do. So the cold fronts tend to catch up to warm fronts, and we get combinations that look like this. And you can see sort of there's two different subtypes depending on which type of cold air in the two colliding fronts, which one's actually colder than the other, to determine whether it looks more like a cold front and you get cold occlusion, or the coldest air is what's farthest to the west or farthest of what's moving in. Or if you just have cool air and the coldest air is what was there initially, it is something called a warm occlusion. And either one of these, they're both denoted with a purple line with alternating triangles and half circles when you see an occluded front on a map. And if you're just looking at this line, essentially where this boundary happens on the surface, you can't quite tell because, again, on a surface, there's just enough information to tell between two different air masses. To know whether it's actually a occluded front, a sort of combination or collision of two different fronts together, you have to have a 3D view like this cross section and your typical surface analysis to know there's warm air above that sort of got pinched off from the surface, or you have to have just a broader sense of what's been happening over space and time, where you have adjoining or colliding warm fronts or cold fronts that you know had to have collided to form an occluded front. And so that can look something like this, where you have your warm air mass over here, your cool air mass sort of over here, and a generally cold air mass over here. So we end up getting an occluded front, and then where the warmest part is still on the surface, we get our previously discussed cold front and warm front. Another feature that's worth mentioning, another kind of front, if you take the definition of a front being contrasting air masses rather than just temperature changes, we get something called dry lines. And these, again, the typical fronts we talked about previously, your warm front, cold front, stationary front, occluded front, those all come to do with temperature contrasts. But the key thing about these boundaries between air masses is really not just its temperature, but its density. So dry lines are special in that they are more of sharp contrasts in moisture. The temperature really doesn't matter that much. Temperature is close to the same when it comes to a dry line. It creates its density contrasts through moisture. And again, recalling previous videos, dry air is more dense at the same temperature than moist air is. And sometimes it's even, if your temperature contrasts are small, dry air can even be a little bit warmer than moist air is, and it can still be denser. So the dry air is on the side that tends to control the boundary behavior because, again, it's the dense air in the contrast between the two air masses. If we were to see this on a map, it looks kind of like what you see over here, where you have a brown line with half circles. In the US, where these typically occur is more in the southern plains, where you can get similar temperature air, but with strong moisture differences from moist air coming up from the Gulf of Mexico and dry air coming from the Southwest United States. But why they're important for a severe and hazardous weather class is that they're often associated with severe thunderstorms and particularly tornadoes, because the shear profiles that develop along dry lines, and we'll talk about shear as an ingredient for severe thunderstorms, the type of shear that develops along dry lines is especially conducive to the formation of tornadoes. But those are details for a coming video. So now sort of looking at these in a little broader context and connecting it to the kind of things we saw in the previous video on scales of weather. These fronts tend to be associated with larger scale systems, which go back to the kinds of flows that we see in the general circulation and the patterns that we see, troughs and ridges, in the atmosphere. So again, I sort of talked about it before. High pressure systems in the northern hemisphere rotate in a clockwise direction. There tend to be divergent airflow that's rotating around the high pressure centers. And they are located below regions of convergence in the upper atmosphere. If we look at low pressure systems, sort of the opposite happens. They're more convergent at low levels. Their rotation, northern hemisphere, is counterclockwise. That would be flipped to clockwise in the southern hemisphere. And they're located below regions of maximum divergence in upper level flow. But you sort of notice this conceptual diagram has the fronts that we just talked about. There's this warm front up here and this cold front over here. So the main kind of these large-scale systems that we talk about are referred to as mid-latitude cyclones, and they're associated with low-pressure systems. So we get these low-pressure systems we call cyclones. In the northern hemisphere, again, they are counterclockwise rotating systems. So we'll go in and talk about the main conceptual model that we use to talk about these low pressure systems or these mid-latitude cyclones. As we see, the US is in mid-latitudes, so it makes sense to talk about these kinds of mid-latitude cyclones. And this model that is most commonly used as a way of understanding these types of systems is the Norwegian cyclone model. And it generally has 4 stages that I'll talk about here. The initial stage, seen over here to the left, is where we have some kind of pre-existing gradient of temperature, or even a stationary front if this is a relatively sharp boundary between different air masses. What ends up happening is when a upper level divergence area tends to come over this contrast, that upper level divergence can tend to force or tend to create a modest low pressure near the surface. And what that ends up happening is the low pressure near the surface, because of pressure gradient force, tends to induce an initial wind flow. And that's what gets this process started, bringing us into the formation stage, or this stage 2, where as the surface low tends to interact with the temperature gradients near the surface, we get well-defined fronts, because now you're getting low pressure causing air movement, and the air movement along with the temperature gradients means that you have moving air masses, which are fronts. And based on how things are positioned, usually in the mid-latitudes, in the northern hemisphere, you tend to get a shape that looks like this, where you have a low pressure system. Your cold air is rushing out along this side, so that forms a cold front here. Your warm air that was down here is now in this sector right here, so you have your warm air. And then that has a boundary with the other cold air to the north, and so you have a warm front over here. And this is where you have clearly separate cold fronts and warm fronts. And this is where a lot of dynamic feedbacks, you can take a more upper level meteorology course to talk about the physical details that go into this, but there's a lot of feedbacks that go on so that the lower level tends to affect or impact the upper levels, and the upper level tends to impact the lower level. And it's a positive feedback cycle that continue to cause the system to strengthen. Once we're really strengthening the system, we reach the third stage that we call the mature stage. Here, the cold front typically, because the cold front moves faster than the warm front, begins to catch up with the warm front near the low, and it begins to form an occluded front in the region that's closest to the low pressure center. The feedbacks continue, and it continues strengthening through this mature stage. And here you have air masses that are clearly rotating around the surface low. So you get this rotating cold air coming around, causing this cold front. You get the ever shrinking or smaller section of warm air in between, and then the warm front over here. And while the mature stage is happening, you have all the different things we talked about before with these different types of front happening. So you can get thunderstorms and precipitation forming along the cold front, where you get sort of this wedge of cold air coming in, forcing this warm air to go upward and cause precipitation and systems develop. Over here on the warm front, you get the cold air acting like a ramp. So as long as the warm air is moving up and along that boundary, you can get precipitation, and generally broad areas of precipitation north of the warm front. And that brings us to the fourth and final stage of the Norwegian cyclone model, dissipating stage. So here, the occluded front has formed, and it is at its longest extent in this whole process because most of the cold front has catched up with a large portion of the warm front. Here, the low level and upper level circulations become cut off from each other, and sometimes they become wrapped up in themselves. So they can no longer continue those dynamic feedback processes. So there's no more strengthening. So it tends to start dissipating and weakening instead. And as this weakens, as the intensity of this low pressure center begins to decrease and it tends to equalize with the pressures around it, the system is considered to be weakening and the air masses are mixing, and so your fronts end up becoming less well defined and the system eventually dies off and dissipates away completely. So that ends our little 4-step conceptual model of how these mid-latitude cyclones, these large-scale low-pressure systems in the mid-latitudes, tend to behave, which is the last thing we're talking about in this section. And to conclude, sort of as a general picture of what the weather looks like around one of these systems. It is a very common signature that pay attention to the weather across the U.S. You probably see these types of things come around often, where you have a low pressure system, you have a line of showers and thunderstorms along a cold front, and then you have a warm front stretching out east and west, and broad, definitely usually the broadest areas of precipitation are to the north of the warm front over here, but there's also some precipitation that sort of wraps around to the western side of the low pressure center. And you see sort of these things, annotations written in here. If this is in a transition season where it's both warm enough to get showers and thunderstorms and liquid precipitation close to the warm front, but it's cold enough that you can get frozen precipitation farther north, you can get snow in this wraparound region, and then a cascading series of warm to cold types of precipitation along the warm front, and then definitely more liquid and rain precipitation along the cold front, where you're all forming along this warm sector where the warm air mass is. So that wraps up this video and this week's material. All of the usual weekly content, the discussion post and the quiz, are up, so please look on Canvas, make sure you're following through with completing those items. And sort of again, another apologies. Things have been sort of tough for me personally. So the schedule for getting all this material up has been kind of wacky the past couple weeks. My plan and my hope is that I can be more consistent in this and get a chance to work ahead on the material to try having a more consistent schedule and all of this going forward. That's what I'm going to try shooting for. In any case, what we'll be seeing next week as far as content goes, we're getting into, I've talked about this a lot, the actual severe and hazardous weather phenomena portion of the course, where we're talking about different types of severe and hazardous weather in detail. We're finally done with the background that we need to understand all of that. Coming up next week. So I will see you then.